This is for A3 Day 1. You've done the Play-Doh activity or parts of it. You've been working with the idea of volume of a solid that we can see the base of and the cross sections of. So what you have on your notes then is the definition that calculus uses for one way to get volume of a solid. The volume of a solid is if we integrate or take the antiderivative and evaluate it, the area from A to B, we can get the volume of the solid. So as we go through and we do this without Play-Doh and things like that, one technique that we're going to start with, and we'll do other techniques next week, is to sketch the solid in a typical cross-section. You might only sketch one or the other if you can visualize it. Find the formula for area of the generic cross-section, not a specific one, but for any cross-section perpendicular to the specific axis that they mentioned. And then use calculus to use integrals and find the volume. So some helpful formulas from what you did last night in the quick review. If you haven't done them, go do them first so you understand where they come from. If you have already done them, then you could keep going. If you haven't, pause, go look and see what we're talking about and come back. And these will come up, and these are geometry formulas. These are geometry formulas moved around so that if you know the side length of something, you could find the area of that cross section, which will help. Pause this if you need to. Work with those if you need to. There are certainly other formulas that are equivalent that will do the same thing. So the example we're going to go through together and pause this and work out the pieces that don't make as much sense to you so that you slow it down, is to find the volume of a solid whose base is bound by the graphs listed. So pause the video, put those three equations, lines in on your graph, your f of x, g of x, and that line x equals 0, which is the y-axis, and then come back. Okay, when you come back, your graph should look like what I have here, and what I've shaded in yellow is the base of the solid, think about the Play-Doh, that you would stand the cross sections on. For part A, it says the cross sections are perpendicular to the x-axis, so that means we'll be integrating in terms of x, and that they're each squares. So I've got a rough picture of what that solid could look like. Okay, it'd be a pyramid where each layer of that perpendicular to the x-axis would be a square. And if you just want to think about what one section looks like, we know that each cross section, the thing we want to get area for, is a square. We need to come up with a formula for its area in terms of the situation that we have. And what I'm noting is that if I put the bottom of my square up onto the base, it would stand up along that segment I just drew. Basically, it's going from the f of x function down to the g of x function, and that would be its side length. So as I'm thinking about what makes the length of this particular square, I would want the value for f at a particular x on that blue function, subtract the value for g at that particular x, and that would give me the length of that segment that I would like to use as my square. So what that does is that gives my square a side length of, and put your formulas in, a side length of 1 minus half an x minus -1 plus half an x. Simplifying this as much as you can would be a very good idea. So as you simplify that and pause the video to do that, your side length for that square is 2 minus x. So as we go to get area for that square then, for that particular section, okay, I would do area of a square, which is side squared, so 2 minus x quantity squared. Just while we have a moment, I would work that out so that you have a polynomial that will be easy to do with or without a calculator. This one we're going to do with, but you could then at least think through how you would do the calculus without on the ones on homework tonight that are without. So there's the area expression. So in order to get volume for this particular solid, the solid formed by those square cross sections all along that base, I would want to take the definite integral from an x of 0 to an x of 2 of that area function. And just for the sake of notes today, so you can get the big idea about area and focus on that more than the calculus, at least in examples, you could go to use your numerical approximation off a calculator. And we'd be talking cubic units because now we're talking volume. Alright, the next part is gonna use that same base, but ask us to do cross sections that are a different shape. Therefore, the volume will be different of the solids. So in part B, it says the cross section's perpendicular to the x-axis, and that's important. If that's switched over perpendicular to the y-axis or to any other line, we'd have to think about what that would change and what our sections in our calculus would look like. It says they're each going to be semicircles. So as I go back to what I would know about one individual section, what I would know about each individual section as that semicircle is if I go back a page for a minute, that means that each individual section is going to be standing up on this picture right here. So the bottom of my semicircle would be that same 2 minus x number that the bottom of my square was, okay, that we found in the last one. But when I get area of a circle, or as half a circle, I really want to use radius. So if that's the diameter, radius on this circle then is 1 minus half an x. I just divided that diameter by 2. So that the area for that semicircle slice, that area of the section that we're talking about that would be perpendicular to the x-axis and standing up, would be half a circle, so half pi, and then I want to square my radius. And that's my radius squared. So that function would serve as the generic area for any of those slices. So then volume of the solid would be the definite integral from, and we're using 0 to 2 because those are the bounds of that graph that those sections are standing on. So not every problem would be 0 to 2, but every one from that same base would be. I'm going to put my area formula in, again, integrating with respect to x because the sections are all standing perpendicular to the x-axis. And again, we could simplify this and use some good calculus and do this. For the moment, we'll let you numerically approximate and double check cubic units. Please watch how you're entering all the parentheses and things that are necessary so that if you're using the calculator as a shortcut tool to your calculus, you're still getting accurate answers. And the last part of the example, we are doing all ones that are perpendicular to the x. You'll see in homework one of them has sections perpendicular to the y, so you'll be integrating with respect to y and writing all of your equations in x equals form so that they're in terms of y. This last one, the cross sections are perpendicular to the x-axis, so again, that's important to note on every problem that you do, and they're equilateral triangles. So I drew a rough version of what that solid would look like along that same triangular base. So each section then, as an equilateral triangle, is going to be standing on that x-axis, and again, standing on that same 2 minus x length. Now you have two choices for how to get your area for your generic triangular section here, and one choice would be to go ahead and do some geometry. The other would be to go back to that formulas page, but you're going to need to make sure you can do this without notes or anything like that and get that area for your triangles. So you have two ways to get the area. If you went back to special right triangles on this triangle, this base here would be 1 minus half an x. And because this is the 30-degree angle in the equilateral, this would be the square root of 3 times that side length. So you could use that then to get area for the entire triangle. If you did that then, you'd be looking at something like area for that entire triangle is 1/2, base of 2 minus x, height of square root of 3 times 1 minus half an x. Right here, that's equivalent to this. So this would come out square root of 3 times, forgive the bell there, times 1 minus 1/2 x quantity squared, which would be one you could absolutely use. If you go back to the formulas that you found in that quick review, the other way you could get area for that one would be to use the formula of square root of 3 over 4, okay, and that's for all equilateral triangles, times its base length squared. Each of these, this and this, are absolutely algebraically equivalent, and you could use either one, and you can test it, in order to get the volume. So volume for that entire solid, definite integral from 0 to 2 of, and whichever one of the two you prefer, square root of 3 times the quantity 1 minus half x squared, again, make sure you've got your differential, and that's gonna come out around 1.155 cubic units. So as you are working with all of this in the homework tonight, make sure that you're not leaving out your calculus, make sure that you're paying attention to whether you can use a calculator or not on a particular problem, and show all your work.